So I want to wish you a very happy chocolate mint day. To me, that means chocolate mint ice cream tonight with my family. If that's what it means to you, whether you eat it with your family or you eat it all by yourself, whatever makes your heart happy. Or if you don't like chocolate mint, then do whatever you need to do. But anyway, I love chocolate mint day. Let me tell you a couple of things logistically, and then we'll jump into the warm-up problem, which you certainly can't read from the back, but I just put it here so that I don't forget what I'm doing. First of all, hopefully you got an email from me with an invitation. Did you get it? Yeah, an invitation to come hang out with me for a party, a data analysis party during Liberty Time right here today, okay? The reason that I wanted to do that is that I know that some of you were kind of feeling a little anxious about the rotational acceleration lab and the analysis that I'm asking you to do. And so I thought, why not just bring everybody in and do it? So if you're free during Liberty Time today, come on in. If you're not and you want to come in and talk to me other times, that's totally fine. But if you and your partner can come in and work, you can get a bunch of it done today during Liberty Time. So I wanted to extend that invitation to you. If you need a pass, let me know and I'm happy to write it for you. Okay. Today is the last day of new content for Unit 7. So just be aware of that. We are doing angular momentum today, and I am going to give you some workbook pages at the end of the day today. Tomorrow is a review day, and then Friday is the Unit 7 test. Okay, I will also get your multiple choice questions hopefully back to you today. If not, then for sure on Thursday. It just kind of depends on the timing of the day. So today we're going to do a warm-up, and then we're going to fill out that gold chart that you have that has a couple more boxes that need to be filled in. Lucy's like, I need to fill them in. I know, it's so exciting, right? So we're going to do that, and we'll do some problems, and it'll be great. Okay, so what I need you to do right now is take a look at this problem up here. I don't think that you've done it yet. It's actually from an AP workbook problem. It's like the back of a page, but whether you've done it or not, it's still a good situation, a good question. I'm going to read it for you just in case it's hard to see in the back there. It says a car company is testing its safety features by crashing cars into barriers at its testing facility. The cars are all the same size and shape, but they're moving at different speeds and have different masses. Assume that the barriers are all identical and exert the same constant force. The question says to rank the time it takes the cars to stop if the barriers apply the same constant force. Okay, so it's a ranking task essentially, just not written by the ranking task people. You might say, we're not doing any rotating. That's okay. There's a reason that I'm giving you this ranking task today, okay? So you might need to look back at your notes. You might need to look back at your equation sheets. Absolutely talk to one another, and then we will regroup in a couple minutes. Sound good? Awesome. All right. Let's do it, shall we? Let's do some physics. Let's discuss what's going on here. Does anybody want to share their ranking with us? I don't mean it that way. Who would like to share their ranking with us? Lots of people had good answers. I heard lots of answers. Go for it, Emma. What you got? D is greater than A equals C. Is that what you said? Okay, is greater than B. How do we feel about that answer? Eden likes that answer. I see lots of other nodding heads. Okay, so that is the ranking. And then, gosh darn it, we have to justify it, right? Not just because I said so, but what physics principle gets you there? There are a few different choices. I'm just curious which one you used. What physics principle gets you there? Tony, what'd you guys do? Momentum. Tell me more. I heard the word. I'm going to write it down because it's a good word to write down. But if you were taking a test and you just wrote momentum, that probably would not be sufficient to earn you points. So expand on that, please. It says in a few short sentences, not a word. Okay, so the greater the momentum, the greater the time. Okay, how do you know that? And you can totally like make somebody else talk to you. I'm not trying to put you on the spot. Or you can just power through and do it. Yeah. It is. F times change in T, or F delta T, is equal to M times delta V. Yeah, this is a big deal thing. Do you remember? Does anyone remember what this is called? It does start with an I. You're exactly right. You better remember what it's called? Impulse. This is the impulse momentum theorem. Indeed it is. So momentum leads us to this idea that the bigger the momentum, the bigger the change in time, which is really because it's the bigger the change in momentum, right? But all of the momenta at the end for each of those cars is how much? 0, because it comes to a stop, so the velocity is 0. And the forces are all the same, so as m delta v goes up, delta t goes up. Yeah, impulse momentum theorem. This comes from Newton's second law, okay? But it's just another way to look at it. We're going to jump in right here with this on our goal. Actually, I should pause and ask. Are y'all okay with that? Okay, good. Now we can jump in and finish up that gold sheet so that Lucy feels like things are complete. Now, we actually did this row right here, the next row that we need to fill in. We just didn't get it filled in. So let's do that real quick. We talked about it on Friday on that late start day. We just didn't get it filled in. So kinetic energy, remember that middle column, or this first column that we're filling in, is the translational column, right? So it's just translational motion or straight line motion. How do you quantify kinetic energy in terms of translational motion? K sub T is equal to, what did you say? 1/2 mv squared. Everybody happy? Yay. Okay. What are the units for it? It is. It's true. Okay. This is the one that we talked about. We rolled some things down the ramp. We talked about a bunch of things. You worked on some problems. How do we quantify rotational kinetic energy? K sub R. Yeah, it's true. What are the units? That's a good question. Should we figure that out real quick? Would that be a good choice, a good thing to do? Let's do that right over here. I'm just going to write it down over here so I don't lose my spot. So the rotational kinetic energy, you've got 1/2 I omega squared. I'm going to give you 1 minute with your teammates to see if you can figure it out. Remember, if you're stuck and you're not sure, just break it down. What are the units of this? What are the units of this? If you don't remember what I is, then figure out what that is. You can do this. I know you can. Just going to give you 1 minute, have a quick conversation. All right. Okay, so what is I? I is mr squared, right? Oh, sad. There you go. And so m is measured in kilograms. R is measured in meters, so that's going to be meters squared. What's omega? Radians per second. We're going to square it, so it's going to be radians squared per second squared, right? Okay, so we got a kilogram meter squared times radian per second all squared. What's that? Remember we talked about how radians are nothing? They're not anything, right? You're nothing. It's just a ratio. It's just a placeholder for a ratio. So we can get rid of the radians. So really this is going to be kilogram meter squared per second squared. So that's nicer. What's that? Do you know? What'd you say? It's a Newton meter. It is, because a Newton is, remember, so if you're like, I don't remember how to do this, I always jump back. F equals ma, right? Y'all know that. F is measured in newtons, mass is measured in kilograms, acceleration is meters per second squared. So a Newton is a kilogram meter per second squared. So I've got a kilogram, I've got 2 meters in there per second squared, so one of them's got to be pulled out. So this is really a Newton meter. And hey, friends, what's a Newton meter? It's a It's a joule. Do you believe me or no? No. Now we talked about this. We did. I recorded it, but I'm going to say it again because it's really important. So we brought it up. I want to make sure you get this because this is a super important concept that you need to know. Okay? When calculating something like work, you apply a force over a distance, right? And the force and the distance have to be what? Do you remember? If you're applying a force over a distance, I'm totally stealing this from you. I'm going to do work on this phone. I'm going to apply a force over a distance. Am I doing work as I lift that object up? Yes. Which direction is my force? Point with your finger. Which one am I pushing? And talk to me about my displacement. Where's that going? Okay. Am I doing work? Yes. Okay. So tell me about my force and my distance. What do they have to be? Say loud. Parallel. They have to be parallel. When you're doing work, it's force and distance, where the force and the distance have to be parallel. We're going to write this down. You can write this on the back somewhere. Don't forget this. This is important stuff. And you know that May 7th is not slowing any down. So let's just write this down. So work is force times distance, where the force and the distance must be parallel. Because remember, an object like this, and I do this, am I doing any work? Am I doing any work right now? No. How do I remember that? Because if I'm doing work, I have to be changing the energy, right? Work energy theorem, do you remember this? Work equals change in energy. I'm not changing, if I'm moving at a constant speed, I'm not changing its kinetic energy. And I'm not changing its gravitational potential energy. There are no springs involved. So I'm not changing the energy, which means I'm not doing any work. We doing okay so far? Okay. Which way am I pushing right now? Which way am I applying a force? Up. But my displacement is horizontal. Okay. So am I doing any work? Indeed, I'm not. Okay. So work is a force times the distance, where the force and the distance have to be parallel. Okay. Totally separate from that, in another universe, or just when we're talking about rotation, we've got torque, which is also a force applied some distance away from an axis of rotation. Okay, so I'm going to remind us here in the work, if I'm holding an object and I'm lifting it from here, h equals 0 to h is not 0, I'm applying a force over some sort of distance. Work is done because I've got to get a force times distance where they're parallel. If I'm applying a torque, so I'm just looking at like a door handle here, okay? If I apply a force like this, parallel to the distance I would measure, am I going to get any torque there, friends? No. How do I get torque? Has to be perpendicular, right? So the force, in order to get a torque, needs to be perpendicular to the distance from the axis of rotation. Okay, so this is my distance. I'm going to call it a radius just to not confuse us. And that force has to be perpendicular to the radius from the axis of rotation. Okay. If I have a force that acts at an angle, in either of these cases, I have to just take the component that is either parallel or perpendicular. You with me there? I have to take only the component that we're talking about. So the secret thing that's hiding in here is some really deep math. Okay? When you get to upper level math, and by that I mean beyond calculus, there are things, so force has a magnitude and it has a direction, which means it's a vector. Remember we talked about vectors a little bit? Okay? And this distance thing is also a vector because we can measure a magnitude and in some cases a direction. I just tell you that I've got two things that I'm multiplying together, but really it's a secret. Do you want to know what's going on? There are two ways to multiply things. I never told you that in second grade. They told you to multiply, but they never told you there were two different ways. Not very nice. You can do this thing called a dot product between two vectors, or you can do this thing called a cross product between two vectors. And in one case, you get a vector out, and in one case, you get a scalar out. This is really crazy stuff. The reason I'm telling you this is to make sure that you know that finding the work and finding the torque are fundamentally different things. Okay? They're fundamentally different things. When you multiply force times distance here, you get a scalar out. This is just a number. Okay? You get a scalar out. This is just a magnitude. Okay? And when you multiply newtons times meters to get just a scalar, just a magnitude, then holy cow, you get this thing called a joule. But when you do this magical thing called a cross product, there's more to it. There's more to it, but I'm keeping it simple for you. If you multiply this vector by this vector in this funky way, you actually get a vector out, but we're not going to go there because it gets confusing. But the thing to know is that you don't get a scalar out anymore. You get this weird vector thing, and the vector is measured in Newton meters. Okay? So you get the result is a vector. Will all of the stuff that I just told you in the last 5 minutes be on a test? No. The only thing you need to take away from this last 5-minute conversation is that work is measured in joules, or you can write it in Newton meters. Nobody's going to fault you for that. Torque is measured in Newton meters. It is not measured in joules. You with me there? Can't do it. Don't do it. Not going to happen. How are we doing? Okay, we good? It's weird. Thanks for asking the question. I appreciate it. All right. Now let's do new stuff, shall we? Sure. Questions about that before I move on? Okay. All right. Momentum. Did you notice that I spelled momentum funny here? Well, I didn't. What's up with that? Well, I'll tell you what's up with that. There's a reason for it. So there are a couple of things that we're going to write down. So here's the thing. Whoa, hello. I just want it to be really big. When we're talking about translational momentum, then we spell it with a, whoa, oh my gosh. Like, seriously? Come on, team. All right, let's see if I can put my hand down here and actually, I'm going to cry. I just want to do physics. Let me do physics, please. There we go. Okay. We've got this thing called momentum with a P, right? And it comes from the impulse momentum theorem. This is why we did that last question, or that first warm-up question, I mean. F delta T is equal to M delta V, okay? You know that this part right here is what we know and love as momentum. The other thing that's really important to know about momentum is that if you have a closed system means there are no outside forces acting, right? If you have a closed system, what do you know about the momentum of the system? Even if there are interactions, what's that? It's always conserved, right? Okay. So, oh my goodness. What's going on here? I'm going to say if there are no outside forces, or we could say if we're talking about a closed system, then we know that momentum is conserved. Momentum beginning, momentum at the end, it's all the same. We can write ourselves a little note here and say that means that delta P is equal to 0. We spent a lot of time doing these problems. We did some stuff, we did some labs, it was great. Okay. Hey, what are the units for momentum, by the way, real quick? So we got it written down. You're like, I don't know. Figure it out. Figure it out here or here. You guys can do this. You have the ability. You have the wit to do it. You can do it. What are the units for momentum, friends? What is it? I'm not gonna. I want to engage with you. What's F measured in? Newtons. What's T measured in? Seconds. So what's impulse measured in? So what's momentum measured in? in seconds, or what's m measured in? V is in meters per second. So you can write this as either newtons times seconds or kilogram meter per second. It's the same thing. Okay. All right. So it may not surprise you, given that I have it on this chart, that there might be a rotational equivalent to this whole thing, right? I'm going to do this on the side here, or you could do it on the back, but we're going to kind of walk through this and make sure we really get where this is coming from, because it's important. Here we go. So F net times T, we know, is equal to delta P, right? If I want to get the rotational equivalent to that, I just need the rotational equivalent to everything. What's the rotational equivalent to force? Torque, right? Whoa, I don't know why it's like decided to just be goofy today. I'm sorry. Torque net. Time is still time, right? So we're just going to go ahead and leave that there. Hey, I'm going to write this over here. Delta P really means M delta V. What is the rotational equivalent for M? If you're not sure, go back and look. You've got it on your sheet. That's why we have this sheet. What is that? What is the thing called? Moment of inertia. And we're going to use letter I for moment of inertia. Right? And what is our rotational equivalent for V? Change in, yeah, nice. Change in omega. So this is the impulse momentum theorem. Okay. The one that we know and love. And this right here is also the impulse momentum theorem. Okay. It's the rotational version of the impulse momentum theorem. Net torque, if a net torque is acting over a time, it's going to cause an object to change its angular velocity. That's all we're saying. If a net torque is acting over a time, it's going to cause an object to change its angular velocity. No big deal. Given the way I've written this, you may be able to predict what letter we use for angular momentum. What do you think it is? You're right. It is L. Yes. This is also equivalent to delta L. Okay. Angular momentum is marked with an L. Just like we said for regular momentum, if it's a closed system, the total momentum of a system isn't going to change. Same in this case. If there are no outside forces acting, then the angular momentum of a system will not change. Okay? Same stuff. You guys, this is such a big deal because it's exactly the same. There's a reason that I put these columns right next to each other, right? You understand that one. This one's easy to apply. So here we go. I'm going to write this. I'm actually going to, no, I'll just go ahead and do an orange still. Okay. So this is, so it's kind of like French, but the L is still silent, okay? Oh, I almost put a P there. That would be embarrassing. That would be wrong. So this is angular momentum, and I'm actually going to write it as angular momentum. Just so we don't get confused, okay? So angular momentum changes if you have a net torque acting over a time. It causes a change in angular momentum. And then similarly in our understanding here, if you go back over to the left, if we're in a closed system, if there are no outside forces acting, then we can say, I think I need to add another row to my table next time, okay? That the angular momentum, I'm so used to writing momentum with a P now, is conserved, which means that delta L equals 0. Okay? I'm going to make one more statement about this, and then we're going to do some practice. Okay. So if delta L equals 0, we can write conservation of momentum out in a nice, pretty way, kind of like we do with the collisions, okay? So that means that the angular momentum at the beginning has to be equal to the angular momentum at the end. You with me there? Okay? No change in angular momentum means that these guys have to be equal. L is equal to I omega, so that means that the I times omega initial equals I times omega final. And usually when we were talking about collisions, we were talking about translational motion, we just left M because the mass wasn't going to change. But here's the secret, guys. When we talk about rotation stuff, often the mass changes. And it's one, or not the mass, excuse me, the moment of inertia changes. And that's what causes things to change. So I actually have to put an initial and a final there as well. Okay? Here's why. If delta I, or I should say, if I increases, the moment of inertia increases. That means that the mass gets further away from the axis of rotation. What does that mean about the angular velocity? What do you think? If I goes up, what would have to happen to omega? It would have to go down. And similarly, the opposite is true. Okay? We're going to make sure that this is true. I need a volunteer, and I kind of want to pick. That's why I signed you up. So you're welcome. All right. So I just want to let you know what the rest of the plan is for the day. Okay, we've got about 10 minutes, and I want to just let you know kind of where we're at, what we've got going on. So we have done everything that I need you to do in terms of seeing that. I mean, that is the demo. It's pretty great. There's a great video that I posted on Canvas that shows ice skaters doing the same thing. If you ever watch at the end of an ice skating routine, they always do it at the end, like they've already done all their jumps and everything. At the very end, they start spinning and they pull their arms in, right? And then and they go, and it's like, whoa, it's crazy. Yeah. So that's what we're talking about there. Okay. We can also apply some math to it to do some problems. So I got 4 problems for you to work, okay? And I was going to do something a little more like organized and whatever, but I really just feel like you guys need to try it out. Do what works for you, okay? So I've got them. I can work on them with you if you want, but I will tell you that I also did post all of the solutions up on Canvas already. Okay, I already got that done. Yes. So that's done. And then I also have for you a few workbook pages, so I'll hand those out to you as well, okay? I'm going to let you work as long as you're actually working for the next 10 minutes. That sound like a fair deal? Okay. Questions you have for me right now? If I can get them, yeah, I'll get them for. All right.